Welcome to this course. In this video, I will show you the app that we're going to build during this class. This is the Mars Rover Photo Explorer app. So we will display photos taken by the rover on Mars. On the second part, we're going to explore the NASA API that gives us those data. Start with a screen of rovers sent to Mars: Curiosity, Opportunity, and Spirit. If I click on a rover, I will get all the day of the mission, so organized by sol and descending, so the most recent on top. If I click on a sol date, I will get the list of photos taken that day. So this is the photo for Perseverance. And if I choose to save a photo, I can click on it, and the save icon change and it's full. And I can access to the save photos through the bottom nav when I can get all the previously saved photos. We'll explain how we're going to use the NASA API to get data inside the rover Perseverance app. So on this first screen, when I click on the rover Perseverance, I send this request. So this is a request over the api.nasa.gov website with the API Mars Rover Mass Photos API v1 manifest. So this API will give back all the sol for the mission. This is the rover name. You can change it to Perseverance. And this is the demo key that it is required to reach the API. You can create your own API key on the NASA API website. And the data that I will be looking at is the sol number that you can see over there, the number of total photos I can see there, and the Earth date that corresponding to that sol, which is now in 2023, May 27th. And for the last sol, we have only 2 photos, and you can see that. And now if I go to the first page, if I click on it, we have got 2 photos, and this corresponds to this API called rovers with the rover name in the path and the photo. And at the end of the path, I've got the sol that corresponds to the sol that we want. And you can see that I get a list of photos with the camera full name, so Media Skycam. And I get a link to an image that is, well, the image of the rovers, the image I want to display. If I get back to more photos, I will change the sol, and we will get the same image. If I open there, you will get the image. How we can use NASA API to get photos from Mars. So let's jump to the next step. Hi everyone, in this video I want to explain how to create the perfect Android app architectures with 4 layers, 1 data layer, 1 view model, and 1 activity with Jetpack Compose element. The data layer will contain our retrofit interface and remote models. It will also contain room interface and local model. In the repository, we will use combine to combine those data from 2 sources. The repository will be also responsible to convert local model and remote model to UI model. The view model will be linked to the lifecycle of the Android app by using ViewModel from the Jetpack Compose library. The activity will contain the compose code and call the view model. Each layer will know the one on the right. The data will navigate from the right to the left in a collected flow. This strategy will allow us to test the repository by mocking retrofit and home classes. Only the repository will know data model and UI model, as it is responsible to convert those. As the introduction is done, we will look at the third screen of the app as it combines data from the remote model and local model For a Mars rover photo, we will save DID, rover name, image URL, sol, update, camera full name in a table called rover photo. The DAO is created with a SQL request to get all the IDs saved. The function returns a flow of list of int with all the IDs saved. For retrofit, we use the suspend function by using the annotation get. This function will return the remote model. The remote model is used to parse the JSON of the remote request. The UI model represents three states: error, loading, and success. For the success, we have the UI model in it. The UI model will be used by the activities and compose elements, ViewModel, and repositories. Data layers should never know this UI model. The repository emits a rover photo UI state. If an error occurs during the remote request, we will emit an error. When the request is pending, we will emit a loading state. First, we call the function retrofit inside a flow. The result is emitted when the response is received. If the request fails, null is emitted. Secondly, we combine the data from the database and from the request by using combine. We use combine on a flow of the database and pass the network as a parameter. Combine emits a new flow each time a new flow of its two combined parameter is emitted. For example, each time the database changes, a new photo is saved, a new UI model will be emitted. The isSave variable is defined to true if the database contains the photo ID. If getAllRemote Mars rover photo returns null, an error is emitted. The ViewModel exposes a UI state as a state flow. We use a private val to modify it. However, immutable val is readable by an external component. The function in the ViewModel starts a coroutine, calls the repository, collects the results, and modifies the immutable state flow. In the compose view or activity, we will use launch effect to avoid calling the function times. A val state is collected by using collect iState with lifecycle. Then a when display the correct view according to the UI states. The state error will display the composable error. The state loading will display the composable loading. The state success will display the photo list. These architectures provide single responsibility principle as the data layer are isolated from the UI layer. Any business code are located in the repository. Allow us to test the repository without Android components and mock the data layers. Create a new project. Name your project Mars Rover. Select API 24 Android 7 to run on 95% of devices. Click Finish. Use the project. We start with a basic view. This basic view is just a text with a preview in it. Create an emulator. In this example, we will create a Pixel 6, but you could choose another device. We will choose the API level 33, that corresponds to Android 13. In the advanced settings, I will increase the internal storage to 4000 megabytes. We don't need to change other settings. Click Finish. Then I will start the simulator. This could take some time. Once ready, click on Run to start the app. Then you can see Hello Android. If I change Android to Mars rover, it will change on the device. Then we will update the dependencies. We will use Boom for Compose by declaring a def called Compose Boom. Boom will define for us the version for Compose for a given date. Then we can remove the version specified. We can update core categories, lifecycle runtime, and activity compose. Then we sync the project and restart it. It should be working as before. To start using Jetpack Compose, we need to use setContent function. Inside, we can call a composable component. We can create composable functions and call them in a setContent. To create a composable function, use the annotation @composable. In this example, a name is passed to modify the text. We also can create a preview. A preview should not have parameters and should be declared with the annotation @preview. To organize the screen, we can use a column. In this example, we will display two texts on top of each other. To organize things horizontally, we can use a row. In this example, the image will be displayed on the left of the two texts. We can use modifier to define padding, sizes, or shapes. In this example, we define a padding for the row. We define a size of 40 dp for the image. A spacer is used to create space between the image and the text. As we are in a row, we should specify the width. A second spacer is used to create a space between two texts of 4 dp. Because we are in a column, we should use the eighth. To create a list, we can use lazy column. Inside items, call the composable for each item in the list. Create a package domain model. Create a class rover UI model. This class will be used to hold the data to be displayed in the list. Change it to a data class. Create a val name. Create a val image. Create a val landing date. Create a val distance. Find images of the rover and copy the 4 images in the drawbar folder. Create a Kotlin class Create a val rover UI model list. This will be a list of rover UI model. Create a rover UI model for perseverance. Specify the name. The image by using air drawable to link the PNG just copied. Specified a landing date. And a distance. Repeat this for the 3 last rovers. Create a new package under UI called View. Create a file rover list. Create a function rover. Add the annotation compose. Create a function rover preview and add the annotation compose too. Add the annotation preview. Inside these functions, call the function rover. Wait for the preview to refresh. Create a card. Add the parameter modifier. And add the padding of 16 dp. Inside this card, create a colon, add also a padding of 16 dp. This colon will display our item in sequence from the top to bottom. Create a text. For the parameter text, add a parameter inside the rover compose function. Add the name Perseverance in the preview. Specify the font weight to bold. Add the font size to 24 sp. Add an image. For the painter parameter, use the function painter resources and specified an ID. Extract the ID in a parameter in the rover compose function. In the modifier, call the metal fill of max width to make the car full width. In the text, align center to center the text. Add a text for the credit. For the text attribute, create the string credit NASA GPL. Add the font size to 8 SP. Add a text for the landing date. Add the landing date parameter to the rover compose functions. Use $landing date to create a string to be displayed. Add the font size to 12 SP. Add the landing date to the preview. Add a text for the distance traveled. hide the parameter distance traveled in a rover compose functions, then use it in the string. Specify the font size to 12 sp. In the main activity, replace greeting with the rover function, clean up the default unused compose function, click Run. After the compilation and the start of the emulator, uCart will be displayed. Open the file rover list. On the top of the file, create a composable function rover list. Create a surface. Material theme, color, scheme, background. This will use the color defined in our theme. Define a modifier with fill max size in order to take all the size of the screen. Create a lazy column. Write items. For the count parameter, use the rover UI model list size. For the item content, call the compose component rover. For each parameters, use the correct item from the rover UI model list with the index. Back in main activity, replace the surface with the rover list. Then clean out some imports. Then rebuild the app. You can see the list in the app. We will look at the documentation for using navigation with Compose. First, we need to import Navigation Compose. The nav controller is the central API for the Navigation Compose. It is stateful, stack of composable that make up the screen in your app and the stage of its screen. To retrieve it, use remember nav controller. To declare a list of screens, we need to use a nav host. Each composable represents a route and the composable functions to be displayed. To change screens, use navigate to the route. By default, it creates a batch stack. To pass a parameter, it is possible to pass it in the route by using brackets. To extract it, use backtrack angstring argument getString with the name of the parameter. We also can use an optional argument by using the parameter syntax. Create a Kotlin class manifest screen. Change it to a composable functions. Create also a composable functions for the preview. Call the manifest screen function. In the manifest screen composable, create a text with a manifest screen. Go to the Gradle file, make sure Android X navigation compose 253 is added. If not, add it. Create a package nav. Inside, create a Kotlin file navigation. Create an object called destinations. Inside, create a constant val home as a string home. Create another constant manifest with a string manifest. Inside the file, create a class actions with a parameter navController. Create a val home as a function. Inside this function, call navController navigate home. Create another val for the manifest. This will be a function too, but in this case, we have the parameter rover name in the function. Inside the function, name the parameter rover name. Call the function navigate on the nav controller. For the root parameter, create a string manifest/rover name by using $, to concatenate the string. Create a new Kotlin file called navCompose. Inside, create a compatible functions navCompose. Inside the navCompose functions, create a val navController, initialize it with remember navController. Then write mass_rover theme to apply the theme to all composable elements below. Pass your nav controller to the nav controller parameter. For the start destination, specify home. The last parameter is a function. Use composable to create a destinations. For the home, call the rover list. For the manifest, call the manifest screen. Inside the rover list, add a parameter onClick. This parameter will be a function with the rover name as a parameter. Repeat it for the rover functions. Where the rover is created in the list, add the onClick. For the preview, pass an empty function. In the rover function, add clickable. Inside the function, call onClick and pass the parameter rover name. Back in the nav compose file, add actions, initialize it with remember nav controller action nav controller, In the rover list, add a function called actions manifest with the rover name. Back in the main activity, change the set content to use our nav compose. Go back to the navigation file, change the string for the manifest to manifest/rover name. Then start the project. The project will start when we click on a card with change screen. Now we want to pass rover name parameter. In the manifest screen, add a parameter rover name as a string. And add it in the text. Back in the nav compose file, we will read the rover name from the backstack entry and pass it to the manifest screen. Name the function parameter backstack entry. Use backstack entry arguments getString getRoverName in order to get the name of the rover. Rerun the app. Click on the cards and you should see the rover name in the text. In this video, we will look at the Retrofit documentation. Retrofit is a popular library that can make API call. This is the official documentation. It is in Java and we will use Kotlin, but it will help us to understand some features. We can create a request by using the annotation @get. Inside the annotation, specify the path. In this first example, the parameter user is passed by the function, so it will be replaced by the string user. To create an implementation, we need to use the builder. We will use build and create. Then we can call the API. As we will use Coroutine, we will create a suspend function. This will allow us to get directly the result without wrapping in a retrofit call object. It is possible to use @post for a post, and other HTTP verbs are available. It is possible to hardcode the query parameter. We can replace some part of the request by putting it between brackets. We can add a query parameter. We also can add a body using @body. It is possible to add headers. Some are for cache control or user agents. If we need to deal with a connection to a user account, we can use the header authorization. We can also pass multiple parameters by using headers. Many converters are available. They will transform our class in a JSON. In this course, we will use JSON. Use @converterFactory to specify it. We will need to import the lib in a Gradle file. Hilt is a dependency injection library. It will help us to create ViewModel, repository, retrofit classes, and room classes. Hilt provides standard containers for Android classes. First, we need to declare plugins and apply them. If you have a problem, make sure those versions are the same. To use Hilt, we need to have an application with the annotation @Hilt Android app. Don't forget to declare it in the manifest file. For an activity, we need to add @Android entry point. For ViewModel, we need to add @Hilt ViewModel. Then we can use @eject to a custom constructor and pass the parameter. Know how to create the class, and will do it for us. We will use @provise to define how to create retrofit and room classes. To access to an application context, we need to use @application context. Go to the Gradle file for the app. We will import retrofit, write implementation com square retrofit to retrofit, and add $retrofit version. In the build Gradle file for the project, add retrofit version equal to 260. go back to the app Gradle file, add implementations square up retrofit to adapter Eric's Java 2 with the retrofit version, add implementation square up retrofit to converter JSON with the retrofit version, last but not least, add square up OK HTTP3 logging interceptor. Add a variable OK HTTP logging interceptor version. In the project Gradle file, add a variable OK HTTP logging interceptor version, define the version to 4.10.0. Create a new package called service. Inside, create an interface Mars rover manifest service. This interface will contain our retrofit code. In the package service, create a package model. In this package, we will create all data class used for mapping the remote JSON. Create a class called Photo Manifest Remote Model. Transform this class to a data class. Add the field serializable annotation with the string landing date and specify the val landing date as a string. The string defined by the annotation should be the same as the one in a JSON. With the string launch date and specify the val launch date as a string. Add the add field serializable name annotation with the string maxDate and specify the val maxDate as a string. Add the add field serializable name annotation with the string maxSol and specify the val maxSol as a string. Add a val name as a string. Add a val photo as a list of manifest photo remote model. Add the val status as a string. Add the add field serializable name annotation with the string total photo and specify the val total photo as an int. Create a class manifest photo remote model. Modify it to a data class. Add a val cameras as a list of string. Add the add field serializable name annotation with the string earthDate and specify the val earthDate as a string. Add the val sol as an int. Add the add field serializable name annotation with the string total photos and specify the val total photos as an int. Back in the photo manifest remote model, it should be able to resolve manifest photo remote model. Create a class rover manifest remote model. Change it to a data class. add the add field serializable name annotation with the string photo manifest. Add the val photo manifest as a photo manifest remote model. Get back to the Mars rover manifest service. Use the annotation get. Create a suspendable functions get Mars rover manifests. For the parameter, add the annotation as path with the string rover name. And define the parameter rover name as a string. This function will return a rover manifest remote model. In the get annotation, define the path of the URL, Mars Photos API v1 manifest rover name API key demo key. The rover name will be replaced by the parameter. If you have created a key, replace demo key. Create a companion object. Inside, create a constant val base URL. With the value of https api.nasa.gov. Create a function create. It will return a Mars rover manifest service. Create a val logger, initialize it with an HTTP login interceptor. Modify the property level. If the build config is in debug, set it to basic. If not, set it to none. create a val client, initialize it with OK HTTP client builder, add the interceptor to our logger. Then build it. For the return clause, we will create the retrofit service, use retrofit builder, define the base URL with our constant val, define the client with our client, add the converter factory with a JSON converter factory, use create to create it, then build, then use create with the type of mouse rover manifest service. Now we will add Hilt in order to inject our service. In the app Gradle file, add implementation Google Dagger Hilt Android $it version, go to the Gradle file in the project, add it version 2.44, back in the app Gradle file, add kpt Google Dagger Hilt compiler with the Hilt version, add implementations Android X Hilt Navigation Compose 1.0.0, in the bottom of the file, add kpt correct error type to true. On the top of the file, in the plugin sections, add id Kotlin kpt, add also Google Dagger Hilt Android. Gradle file. In the plugin sections, add ID com Google Dagger Hilt Android version 2.44, apply false. Then sync the project. Create a new package, call it DI. Create app module as an object. Add the annotation at module. Add the annotation at installing with the singleton component class. Inside the app module object, hide the annotation provides. Add the functions provide Mars rover manifest service. This function will return a Mars rover manifest service. Use the function create to return a Mars rover manifest service. In the root package, create a class base application. Make it extends application. Add the annotation at Hilt Android app. Go to the manifest. In the application, add Android name and our based application. Add also the internet permission. Add users permission with the permissions android.permission.internet. In the package domain model, create a class rover manifest UI model. This class will be used by the lazy column. Change it to a data class. Create a string sol. Create a string update. create a string photo number, extend this class with comparable, implement the comparable functions, make it return compared to Earth date. On the top of the file, create a sealed class rover manifest UI state. Inside, create a data class success with a list of rover manifest UI model. Make it extended with rover manifest UI state. Create an object loading, make it extend with rover manifest UI state. In the View package, create a file called error. On the top of the file, create a composable function called error. Create a composable function for the preview. View. And name the function's error preview. Inside these functions, call the composable error. In the error composable, create a box, add a text in it. Wait for the preview to refresh. In the res value folder, open the strings XML file. In this file, add the string error with the contents error. Back in the error file, use the string resources to link the text just created. Use err.string.error. Inside the box, specify the modifier parameter with modifier fillMaxWidth, fillMaxHeight. And the content alignment to center. Refresh the preview. You might have to build the app. Create a file loading. Create a composable function loading. create a preview with the name loading preview and call the loading component. Use the annotation add preview inside the loading function, create a column, add a circular progress indicator, add a text. For the text, use string sources, go to string.xml, add loading, back in the loading composable functions, use the string by using string loading, in the colon, add the modifier, set to fill mark width and fill mark height, set the vertical arrangement to center, set the horizontal alignment to center horizontally, once the project is built, open the preview. Create a file manifest list. Create a composable function manifest. This will be one of our items of our list. Create a card. Inside the card, create a column. Inside the column, create 3 texts. Add the parameter rover manifest UI model in the compose function. For the first text, use rover manifest UI model sol. For the second text, use rover manifest UI model update. For the third text, use rover manifest UI model photo number. Go to the strings.xml file. Add a string sol with %s. Following the same principle for earth date and photo number, back in the manifest list, use string resources to replace the string and add the parameter to replace the %s. Repeat this for the earth date and the numbers of photos. Then create a preview. Create a composable functions manifest preview. Call a manifest component with a fake rover manifest UI model. Then have a look of the preview. We will arrange some padding. In the column, add a modifier with a padding of 16 dp. In a card, add also a modifier with a padding of 16 dp. Make the card talking all the width of the screen by using Fill Max Width. Add also a clickable. We will fill that later. On the top of the file, create a composable functions manifest list. Create a surface with the color background of our material theme. Create a modifier with Fill Max Size. Inside, create a lazy column. Write items. Add a parameter in the manifest list functions. Add a list of rover manifest UI model. Back in the function item. For the count, use the size of the rover manifest UI model list. For the item content, create a manifest with the correct index. You can also rename the lambda with the parameter index. Go in the Mars rover ViewModel. Create a private val underscore rover manifest UI state as a mutable state flow of rover manifest UI state. Initialize it with a state loading. Create a val rover manifest UI state as a state flow. Specify the get functions to get the multiple private val. Inside the coroutine, set the underscore rover manifest UI state to loading. In the connect block, set the value to it. Go to the manifest screen. Clean the unused preview. On the top of the compose functions, create a val view state. Initialize it using buy and collect as a state with lifecycle. If you get an error, import it. Then create a when on the view state. For each state, link it to the correct view. Error to error. Loading to loading. Success to manifest list. Refactor rover manifest UI model to rover manifest UI model list to make it more explicit. Then build the app. When you click on a rover, the loading should appear. When the request response is received, the list should be displayed. Inside the package view, create a file photo screen. On the top of the file, create a composable function. Inside, create a text with the value of photo screen. Open the nav package. Open the navigation file. Create a new constant photo with the value of photo/rover name $photo equals sol. In the class action, create a val photo with a parameter rover name as a string and a parameter sol as a string. Then return a function. Name the two parameters. Call the navController navigate function. For the route, create it with the parameters photo/parameter rover name $sol equals parameter sol. Now we will call the unclick action on the manifest card. Inside the manifest list, add a parameter to the function manifest list for the rover name as a string. Add also an onClick function. This function will take two parameters. Repeat the step for the manifest function. Inside the clickable, call onClick with the parameter rover name and the sol. Fix the error inside items where we create the manifest composable by adding the two parameters. Fix the preview by adding an empty rover name and an empty onClick function. Go to the manifest screen. Then pass it to the manifest list. On the nav compose file, add onClick function and call action photo with the rover name and sol. Add also a composable for the photo route. Inside, call photo screen. Then run the project.
Once started, you should be able to change screen when you click on a manifest card. In this part, we will create the request in order to recover photos for a given rover name and sol. First, we need to create a data class to pass the response. Inside the service model, create a class Camera Remote Model. Use add field serialized name, full name, and declare the val full name. This will allow to have a name that matches the decision and another name in the Kotlin code. Create a val ID. Create a val name. Use add field serializer name for the val rover ID. Create a data class rover remote model. Inside, create a val ID. Name and create a val landing date. Use add field serializer name and create a val launch date. Create a val name. Create a val status. Create a new data class photo remote model. Create a val camera as a camera remote model. Use add field serialized name and create a val of date. Create a val ID. Use add field serial name to create a val img src. Create a val rover as a rover remote model. Create a val sol. Create a data class rover photo remote model. Create a val photos as a list of photo remote model. In this example, I have chosen to declare all the value. It is possible to ignore the one that we do not use. Create an interface Mars rover photo service. Use the annotation addGet from Retrofit with the parameter Mars photo API v1 rover rover name photo question mark API key equals demo key. Then create a suspend functions get Mars rover photo. Use the annotation addPass rover name as a string to replace the rover name in the URL path. Use the annotation addQuerySol to add the parameter sol. Make the function to return a rover photo remote model. Create a companion object. Create a constant val base URL with the value of https api.nasa.gov. This URL is the same with the one in the manifest file. Create a function create. This function will return a Mars rover photo service. Create a val logger as an HTTP logging interceptor. Define the logger level according to the build config. Basic if in debug, none if in release. Create a val client. Instantiate an OK HTTP client builder. Hide our logger as an interceptor. Then build. Create a retrofit builder. Add the base URL. Add the clients. Add the converter factory by creating a JSON converter factory. Then build and create by specifying the Mars rover photo service class. In the app module file under the DI package, similar to the manifest, create a function named provide Mars rover photo service using the annotation as provides. Make the function returning a Mars rover photo service. Inside the function, call create. Create a rover photo UI model. Change into data class. add a val ID, add a val rover name, imgsrc, add val sol, add a val update. Add a val camera full name. On the top of the file, create a sealed class rover photo UI state. Create a data class success with a list of rover photo UI model. Extend it with rover photo UI state. Create an object landing and extend it with rover photo UI state. Create an object error and extend it with a rover photo UI state. Inside the data package, create a Mars rover photo repo. Use @inject constructor to create the Mars rover photo service. Create a function getMarsRoverPhoto with a rover name and a sol as a parameter. This will return a flow of rover photo UI states. Add a try catch. Inside the catch, emit a rover photo UI state error. Create a val network result with the result of the get Mars rover photo from the service. emit a rover photo UI state, transform the remote model by using map over photos and create a rover photo UI model. For the ID, use photo ID. For the rover name, use photo rover name. For the image src, use image src. For the sol, use photo sol toString. For the earth date, use photo earth date. For the camera full name, use photo camera full name. Inside UI, create a new package photolist. Create a file Mars rover photo ViewModel. Add the annotation Alt Hilt ViewModel. Add the annotation @inject constructor to inject the Mars rover photo repo. Extend with ViewModel. Create a function getMarsRoverPhoto with the parameter rover name and sol. Start a coroutine on the ViewModel scope. Then call the getMarsRoverPhoto on the repo. Then collect the results. On the photo screen, add a rover name parameter, add a sol parameter, add a Mars rover photo ViewModel parameter. Add an if to verify that the rover name and the sol are not null. Start a launch effect and call the getMarsRover photo on the ViewModel. Open the nav compose file. Use the backstack entry to recover the rover name by using argument getString key rover name. Repeat this operation for the sol by using the key sol. For the ViewModel, use Hilt ViewModel. Then run the app. Once the app has started, select a rover, then a sol. You should be able to see the request and the response in the log. In this video, we will create the new UI for the photo list. Inside View, create a Kotlin-fied photo list. On the top of the file, create a composable functions photo list. create a composable function photo, add the parameter rover photo UI model, create a composable function photo preview with the annotation @preview, inside this function, call the composable photo, for the rover photo UI model parameter, create a fake model with some example value. In the photo compose function, create a card, use a modifier to add a padding of 16 dp, create a column with a padding of 16 dp, inside the column create a text with the value of the rover name from the UI model, add a padding of 16 dp. Create a second text with the string sol and add the parameter sol from the UI model. Create a third text with the string resources earthDate and the earthDate parameter from the UI model. Create a fourth text with the value of the camera full name. In the PhotoList function, add the parameter rover photo UI model list as a list of the UI model. Create a surface. From the color, use the background color from our material theme color scheme. Add the modifier with fill max size to take all the screen size. Create a lazy column. Use items to specify the count with the size of the list. For the item content, create a photo composable with the right item from the correct index. In the Mars rover photo view model, create a private val underscore rover photo UI state as a mutable state of flow of rover photo UI states. initialize it with a loading state, create a val rover photo UI state as the state flow of rover photo UI model, set the get to underscore rover photo UI state. In the get Mars rover photo, before sending the request, set the underscore rover photo UI state value to loading. In the collect, set the value to it. It should be the value collected. In the photo screen, create a val view state, use collect as a state with lifecycle on the Mars rover photo ViewModel rover photo UI state to initialize it. Then use a when over the view state. For the error case called the composable error, for the loading case called the composable loading, for the success called the photo list with the rover photo UI state. Then run the app. Wait the emulator to start or use your phone. When you select a rover and a sol, you should be able to see a list of the information about the photos. For loading images, we will use the Coil library. It will request and save the image for us. We need to import it. Then we can use a composable async image with the URL of the resources in the model parameter. Many options are available for crossfade effect, on error, placeholder. You can also use a modifier. In this part, we will add the photo inside the list created on the previous one. First, go to the Gradle file. Import the Coil library. Use implementation IO Coil KT Coil Compose with the Coil version. Add the Coil version to 2.2.2. Then sync the project. Then go to the photo list. In the composable function, under the text of the row of name, add async image. For the model, use img src of the UI model. For the content description, create a string rover photo. Add a modifier with an height of 300 dp. Then run the app. Display a list of photos for a given rover and sole. You should be able to see pictures of Mars. We will look how to integrate a bottom nav. First, we need to import a list of screens could be defined with a root and a resource ID. The resource ID is the drawable to be displayed in the bottom nav. We need to create a scaffold and use the parameter bottom nav. Inside, we need to create a bottom navigation compose. For each item, create a bottom navigation item compose. The icon will be the drawable for the icon. The label will be the text under it. Selected will define if the current tab is selected. For the unclick, change the screen. Make sure we clean the backstack. We can use inner padding to create a padding at the bottom of the screen to end the screen on the top of the bottom bar. In this video, we will add a bottom navigation. First, we will add logos. Under the Res Drawable folder, create a new vector asset. Select a local file and open the rover picto. Set the name to IC Mars Rover. Change the dimension to 24 dp. Add a second vector drawable, this time select the clip art. Search Save and select the Save icon. Rename it to AC Save. Then open the navigator file. Add a constant file saved with the value saved. Create a Hilt class screen. In this Hilt class, create a val root as a string. Create a string resources ID as an int. Create a drawable resource drawable ID as an int. Go to the string value file. Create a string rover. Create a string saved. Back in the navigator file, create an object home as a screen. For the root parameter, declare a string home. Use the string rover for the second parameter. For the third parameter, use the drawable IC Mars rover. Repeat this for the object saved with the string saved and the drawable IC saved. Create a file photo list save screen. Create a composable function photo list save. Add a text with the string saved photo. Go in the nav compose file. Inside the nav host, under composable photo, create a composable for the save screen. Composable photo list save screen. On the top of the file, create val items. This list is a list of screens with home and saved. In the Mars rover theme, put everything inside the scaffold. Correct the error by adding the annotation at experimental material 3 APA. Rename the lambda parameter to inner padding. Create a modifier with this inner padding. Declare a bottom bar parameter in the scaffold. Inside, create a navigation bar. create a val nav backstack entry by using the current backstack entry as state on the nav controller. Use the nav val for the current destination. Use a for each items to create navigation by items according to the list declared for items. For the icon parameter, create an icon. Use painter resources to define the drawable ID. For the content description, use the string resources. For the label, create a text with the string resources. For the selected parameter, your current destination hierarchy to know if the user is on the manifest or a photo screen. Compare the current route with the current screen route. All this logic is used to select home if the user is on home or manifest or photo, and select saved if the user is on a screen saved. For the click function, call navigate on the nav controller to the route. Use Puppet2 to start the destination ID. Set the save state to true. Set the launch single top to true. Set the restore state to true. Then start the app. Now a bottom nav is on the bottom of the screen. You can play with the button to change the screen. If you try to scroll, the bottom of the screen is cropped. We will fix this. In the nav compose file, add a parameter modifier and pass the modifier with the inner padding previously created. Go to the hover list and add the parameter in the compose function. Then use it in a surface that call the function fill max size. On the nav compose, the error should be corrected. Then run the app. Then scroll the rover list. The content should be no more cropped. Do the same for the manifest screen. Add the parameter to the manifest screen function. pass it to the manifest list, the parameter, and use it in the surface. Repeat this for the photo screen. Add the parameter in the photo screen function and pass it to the photo list. In the photo list, use it in the surface. Add it to the photo list save screen. We will use it later. Start the app, find a small list of photos, and verify that the content is not cropped. First, we will look at the room documentation. To find this documentation, search Android Developer Room. Room is used to save local data, then the user can access it while offline. It can also be used to save user information, for example, a progression in a game, or a task for a to-do list. Room provides the advantage to compile the SQL queries, to reduce the boilerplate, and help you to manage upgrade. For the setup, we need to import a few libraries. Room is divided in 3 components: the database that will be our main access point, data entities that will be tables, and DAO that will be used to perform requests on the database. It will manipulate entities objects. To create entities, use the annotation @entity over a data class. Use @primary key to define the primary key. To create a DIO, use the @DIO over an interface. We can do SQL queries. Select is used to retrieve some data from a table. Where is used to filter the results. @insert will add data. Delete will remove some data. For the database, we will need to use @database over an abstract class. We need to specify the list of entities and the version. We must extend this class with room database. We can refer to the DAO with an abstract function. To initialize it, we can use the builder. We want to use asynchronous queries. For the insert and the delete, we will use a suspend function to create a coroutine. For getting the result, we will use flow. To test our database, it is possible to open a shell on an emulator. Then you can use SQLite 3 over the DB file. In this video, we will create a database and write some data in it. First, we need to import room. Go to the Gradle file. Use KPT Android X room compiler. Replace the version with the variable. Add implementations Android X room KTX with the room version. Go to the project Gradle file and add the room version to 251. Sync the project to verify that everything is fine. Create a package DB. Inside, create a file Mars rover saved local model. Modify it to a data class. Add the annotation @entity with the table name to use room. Create a val rover photo it as an int. Use @field serialization name to define a name for the column in the DB. Use @primary key to make it the primary key. Create a val rover name. Create a val mgsrc. create a val sol, create a val update, create a val camera full name. Create a Mars rover state photo DAO as an interface. Use the annotation @DAO from room. Use the annotation @insert to create a suspendable function insert with the local model as a parameter. Specify the onConflict strategy to replace. Use the annotation @delete to create the suspendable function delete with a local model in the parameter. Create a function using the annotation @query. Write the SQL query select rover photo ID from rover photo where sol equals sol and rover name equals rover name. Name the function allSaveID and pass the parameters sol and rover name. Make the function to return a flow of list of ints. This function will help us know if the photo is saved. Create a new Kotlin class Masterclass Save Database. Make it abstract and use the annotation @database. Define the list of entities, for now only the Mars rover saved local model. Set the version to 1. Set the export schema to false. Extend the abstract class with room database. Create an abstract function Mars rover saved photo DAO. This function will return a Mars rover saved photo DAO. Create a companion object. Use the annotation @volatile to create a private val. Name this var instance as a nullable Mars rover save database and initialize it to null. Create a function getInstance with the parameter context. Make this function to return Mars rover save database. Return instant for instance. If it is null, start a synchronized block. In this block, return instant if not null. If null, call a function build database. Use also to set the instance to return the value returned by the function. create this build database function. Use the database builder over the classroom. Pass the application context and the type of Mars rover save database and the name of the DB file. Call the fallback to destructive migration. This will delete the DB when we upgrade the version number. Then code build. In the app module, use add_provide to create a functions provide Mars rover saved photo DAO. Use @application context to pass the context. Return the DIO by using the functions Mars rover save photo DIO after getting an instance of the database. In the Mars rover photo repo, in the constructor, add the Mars rover saved photo DAO. Create a private function get all remote Mars rover photos. Add two parameters rover name and sol. Make this function to return a flow of rover photo remote model. Create a try-catch block. Inside the catch, emit null and change the return type to nullable. create a val network result and initialize it with the Mars rover photo service. Then emit the network results. Empty the getMarsRover photo function. Call the all save IDs on the DAO. Then call combine. Install the get all remote Mars rover photos. Explicit the toLambda parameter with local and remote. If remote is not null, create a rover photo UI state success. Rename the letLambda parameter to rover photo remote model. Then use map rover photos to create a list of rover photo UI model. If the remote model is null, then return the state error. Then pass the parameters to create the rover photo UI model. Then go to the rover photo UI model, add the value isSaved as a boolean, back in the repo, for the isSaved parameter, verify if the local contains the photo ID. Create a new vector asset, search save, and select the save icon. Select Outline. Rename it to IC Saved Outline. Go to the photo list, create a row with a modifier with fill max width, move create an image, use Painter resources, if the photo is saved, use the IC Save icon. If not, use the IC Save Outline icon. For the content description, add the string save icons. Correct the preview by adding true for the isSaved parameter. Then start the app. Go to the list of photos. We can see a save icon. Back to the photo list. In the card modifier, add a clickable. Add a onClick function in the photo composable function. Call this function in the clickable. Add the parameter to the photo list and pass it to the photo function. Fix the preview by adding an empty function. Open the Mars rover photo repo. Create a suspend function save photo with a parameter rover photo UI model. Create a suspend function remove photo with a parameter rover photo UI model. Inside the package domain model, create a rover photo converter. Create a function 2DB model with a UI model in the parameter and a local model as a return to the function. Create a local model. For the rover photo ID, use the UI model ID. For the rover name, use the rover name. For the IMG SRC, use the IMG SRC. For the sol, use sol. For the earth date, use the earth date. For the camera full name, use the camera full name. Back in the Mars rover photo repo, in the save photo function, call the function insert on the DAO. Use 2DB model to convert the UI model to the DB model. In the remove photo function, use the same with the delete function. Open the Mars rover photo view model. Create a function change save status with a UI model as a parameter. Start a coroutine by using launch on the ViewModel scope. Specify the dispatcher to I/O. If the photo is saved, call the remove photo function. If not, call the save photo function. Open the photo function for the last parameter. Inside this function, call change save status of the view model. Then start the app. Play with the app and click on various photos. You can see that the icon saved outline or field is persisted. In this part, we will create the save screen that will display the data from the database. Inside the Mars rover state photo DAO file, create a query select star from rover_photo order by Earth Dead Desk. Name the function getAllSaved and return a flow of a list of Mars rover saved local model. Open the Mars rover photo repo. Create a function getAllSaved that returns a flow of rover photo UI state. Call getAllSaved function from the DIO. Use map over it to iterate over the list. Go to the rover photo converter. Create a function toUIModel. The parameter will be a list of local model. Use map to iterate over the local list. Then create a rover photo UI model with the correct parameter. As this data comes from the database, set the isSave to true. Back in the repo file, use the function toUIModel in the UI success to pass the list of the UI model. Create a package save list under UI. Create a file Mars rover saved ViewModel. Use the annotation @Hilt ViewModel. Use @inject constructor to add the photo repo in the parameter. Extend the class with ViewModel. Create a private val _ Mars photo UI save state as a mutable state flow. Initialize it with the state loading. Create a val Mars photo UI save state. Set the get to _ Mars photo UI save states. Create a function getAllSaved. Start a coroutine on the ViewModel scope and use the dispatcher IO. Call the function getAllSaved from the repo and collect the flow. Inside the collect, set the value of the mutable state flow with the result of the collect. Go to the Mars rover saved ViewModel and copy the change state function. Pass this function is a Mars rover saved ViewModel. Go to the photo saved screen. Add the Mars rover saved ViewModel in the parameter. remove the text, create a val viewState, and use by Mars rover state ViewModel Mars photo UI save state collect as a state with lifecycle. Add the launch effect block, inside call the get saved from the ViewModel, create a when over the viewState, for the error case call the composable error, for the loading case call the composable loading, for the success call the composable photolist, for the list use the data from the viewState. For the onClick, call the change saved status. Then run the app. Go to the nav compose file and add the ViewModel parameter by using Hilt ViewModel. Then rerun the app. This time the app should start. Go to the Save tab. When you click on a photo, the card should be removed from the list. Try to add a few photos to see them in a list of the saved photo.
In this video, we will change the color of the app. We want to personalize it with mask colors. Inside the package UI, open the color.kt file. We will replace purple 80 with an orange 80 and change the color to an orange color. Then I will change the purple gray to a dark orange and change the X decimal for it with 500000. Then we'll change the purple 40 with the orange 40. And change the X for it. I will replace the purple gray 40 with the orange 10 and change the X color to it. I will create a new val called light yellow and create the correct color. I keep pink 40 as I'm happy with that color. This color will define our palette. Feel free to change it if you want to. Now we will apply. Go to theme.kt. I will replace value that we have created. For the dark theme, I will replace primary with orange 80 and the secondary color with dark orange. I will keep the tertiary with pink 80. I will add the surface variant with dark orange. Then I add the on secondary with white color. This value will mainly use for text. For the light theme, define primary orange 40, secondary orange 10, and surface variant little yellow. This surface variant will be used for the surface of the card. Then remove the default commented code. Android 30 define a dynamic color. I don't want to use it, so I will remove them, but you can keep it if you want to. This color will be defined by the user in the settings menu. Now we can clean up some imports. Now we can run the app. Once the app has started, play with the app, you will see new colors. Go to the Android settings and add the dark theme toggle. and activate it. Then get back to the app. You can see new colors as we apply the new theme. You can see that the icon for the save and unsave status is still black, so we will change it now. Go to the res folder. Under Values, open the colors.xml in the Explorer. If you are on Mac, this should be Finder. Move up to the res folder. This will allow us to define specific resources for the dark theme. Go back to the folder Values and copy colors.xml. Paste it into Values Night. Now back in Android Studio, you can see you have two colors.xml values, one for night and one for normal. We will modify them. In the normal color.xml, remove everything else from the black color and rename it to the icon color. In the night color.xml, remove everything except the white color and rename it to icon colors. Then open the drawable IC save, update the tint with the color icon color that we just created. Repeat this operation for the icon IC save outline. Then restart the app. Still in a dark mode, navigate to a photo of Mars. You can see now that the icon saved is white, as the outline too. In this video, we will use a Google font, so we need to create a provider. For creating this provider, we need to create the fontset.xml. This file could be found in the Jetpack Compose sample from Google. I have also included in the resource of this lecture. Then copy this file, we will move it inside the project. Open in the Explorer the folder Values. Create a folder Values v23. Then copy the fontset.xml in it. Back in Android Studio, you can see now the file. Then go to the Google Font website. We will choose the Catnip font. Go to the Catnip page. You can see a preview of the font and download the Catnip font. Extract the zip file. Then select the Catnip Bold, Catnip Light,
catnip medium, catnip regular, and catnip semi-bold. Then copy it. Then go back to Android Studio, directory font, open it in the Explorer and pass the font in it. Once passed, rename the font with no caps lock and only underscore. Back in Android Studio, you can see now the font in the font folder. Open the file tab.kt under UI theme package. Remove the commented code. Create a val provider. This will be a Google font provider. Now we need to import Google Fonts. In the build kernel file, add implementation Android X Compose UI text Google Fonts to import Google Fonts. We do not need to specify the version number, so remove it. Then sync the project. Now we can import Google Fonts. For the provider authority, specify com.google.android.gms.fonts. For the provider package, specify com.google.android.gms. For the certificate, specify the array com Google Android GMS font sets. This will use the value inside the font set.xml. Because Google Font is experimental, we need to fix the warning by adding the annotation opt experimental at test API. Create a val catnip font as a Google font with the name catnip. We will use this to create a catnip font family. Create a val catnip font family. This val will be used to define all the font available in the app. For example, bold, semi-bold, light, etc. Instantiate a font family object. Declare a font by using Google Font catnip font and the font provider with our provider. To resolve font imported. Then create a font with res ID air font catnip regular. The imports are quite complex to resolve. Make sure you have Android X Compose UI Text fonts and Android X UI Text Google Font. Now add the annotation at API as font is experimental. Then create a font with Google Font catnip font provider, and weight light. Also declare a font with res ID air font catnip light with the weight light. Then create a font with the catnip font and the same provider with the weight medium. Use res ID to link the file catnip medium and also the weight medium. For the semi-bold, use the font catnip font and the same provider. Use the font weight semi-bold. Use also the res ID catnip semi-bold and the weight semi-bold. Last, for the bold, use catnip font and the same provider. Use the weight bold. For the res ID, use catnip bolds and also the weight bold. Now we will define the typography, so rename typography with Mars Rover typography as we will use our values. According to Material 3, 5 categories of typography are defined. One is display for very large text, one is header for define our headers, one is title to define the title, one is body to define the body in the app, one is label to define some label. For each category, 3 variants are available: large, medium, and small. We will begin by defining the display large. Use the font family catnip font family. Use the font weight light. Use the font size 57 SP. Use the line 8 64 SP. Specify letter spacings to 0 sp. Specify the display medium. Instantiate a text style. Specify the font family to catnip font family. For the font weight, set it to light. For the font size, specify to 45 sp. The line end to 52 sp. And the letter spacings to 0 sp. Now add the display small, always with the text style. For the font family, use the catnip font family. For the font weight, use normal. For the font size, define it to 36 sp. For the line 8, 44 sp. For the letter spacing, still 0 sp. We will create the headline large. For the font family, still use catnip font family. Specify the font weight to semi-bold. For the font size, specify to 32 sp. For the line 8, specify to 40 sp. And the letter spacing to 0 sp. For the headline medium, use the font family catnip font family. Specify the font weight to semi-bold. Define the font size to 28 sp. Specify the line 8 to 36 sp. Specify the letter spacing to 0 sp. Now we will specify the headline small. For the font family, use catnip font family. For the font weight, use semi-bold. For the font size, use 24 sp. For the line 8, use 32 SP. For the letter spacing, use 0 SP. Now for the turtle large. For the font family, still use the catnip font family. Define the font weight to semi-bold. Define the font size to 22 SP. Define the line 8 to 28 SP. For the letter spacing, set it to 0 SP. For the title medium, again use the font family catnip font family. Set the font weight to semi-bold. Define the font size to 16 SP. Define the line 8 to 24 SP. Set the letter spacing to 0.15 SP. Define the title small. Use the font family catnip font family. Set the font weight to bold. Set the font size to 14 SP. Set the line height to 20 SP. Set the letter spacing to 0.1.sp. Now we will define the body. Start with the body large. For the font family, use catnip font family. Set the font weight to normal. Set the font size to 16 SP. Set the line height to 24 SP. And set the letter spacing to 0.15 SP. For the body medium, set the font family catnip font family. Set the font weight to medium. Set the font size to 14 sp. Set the line height to 20 sp. Set the letter spacing to 0.25.sp. For the body small, set the font family to Catnip font family. Set the font weight to bold. Set the font size to 12 sp. Set the line height to 16 sp. Set the letter spacing to 0.8.sp. For the label large, set the font family to Catnip font family. Set the font weight to semi-bold. Set the font size to 14 sp. Set the line height to 12 sp. Set the letter spacing to 0.1 sp. Set the font family to Catnip font family. Set the font weight to font weight semi-bold. Set the font size to 12 sp. Set the line height to 16 sp. Set the letter spacing to 0.5 sp. For the label small, set the font family to Catnip font family. Set the font weight to semi-bold. Set the font size to 11 sp. Set the line height to 16 sp. Set the letter spacing to 0.5 sp. Now everything is set up, get back to theme.kt and replace typography with mouse hover typography. This will use our typography that we just defined. Now we will apply the typography for all text in the app, starting with the rover list. For the first text, remove the font weight and the font size. Then add style with the value of material theme, typography, headline small. For the credit text, remove the font size. Use material theme, typography, label small. Date, remove the font size. Use material theme, typography, body small. For the distance travel, use also material theme, typography, body small. Don't forget to name the parameter with style. Now on the error.kt file, in the error compose function, use the style body large. Now on the loading.kt file, inside the loading composable function, use the style body large. Now on the manifest list, move to the manifest compose function. I want the text for the sole to be a little bigger than the other, so I will choose title medium. For the second text of the earth date, I will choose body small. For the number of photo, I will also choose body small. I will just format this file to have a better view. Now on the photolist.kt file, move to the photo composable function. For the first text of the rover name, I will define the style to title medium. For the sole text, this will be body small. For the earth date, this will also be body small. And for the camera full name, this is also body small. Then format the file to make it more readable. Now I will start the app to see the result. Wait for the emulator to be ready. Once it is ready, the application will be installed. When the installation has started, page of the app and see that the new typo is now implemented on all screen. For the rover lists, to the loading screen, to the manifest list with the sole bigger than the other text. Also for the photo list. This wraps up this lesson. You can find the source code in the resources of this lecture. In this video, I will create a test for the rover manifest converter. Open the example unit test under the test folder. Run the default unit test and see that the result is correct. Modify the expected result to 5 and see that the test is now failing. Then we will rename example unit test with rover manifest converter test. This name will be more representative of the test we want to run in it. Then we will rename the test addition is correct with should convert rover manifest remote model to rover manifest UI state. Once again, correct naming will allow us to find a file. Then remove the default commands and comment the example assertion. We will divide the test in three parts: given, when, then. The given part will contain all the prerequisites for the test. In this particular example, I will create the rover manifest remote model. The when part will contain the code of the function that we want to test. The then part will contain the assertion with an expected result and the result of the function. We will create a rover manifest remote model and call the constructor of it. For the photo manifest parameter, create a photo manifest remote model. Inside the photo manifest remote model, define the parameter landing date to 2021-02-18. This is the landing. Define the launch date to 2020-06, the launch date of the Perseverance rover. Define the max date and define the max sol. For the name, set up to Perseverance. For the photos, I will define an empty list for now. I will define the status to active. I will set up a number for the total photos. Now in the when clause, set up a val result. Initialize this val by calling the function toUIModel with the parameter rover manifest remote model. In the then part, create a val expected result. Initialize this expected result with a rover manifest UI state success. For the parameter, create an empty list. Then modify the assert equal with the expected result and the result. Then run the test. It should pass because we compare two empty lists. Now inside the rover manifest remote model, I will add a photo. Inside the empty list for the parametered photos, add a manifest photo remote model, define camera as a list of rear as cam left, rear as cam right. Define the RDEV to 2021-02-18. Assault to 0, and the total photo for 54. Rerun the test and see the error. The log said that we had one item in the list, instead an empty list. So we will add an item in the expected result. Create a rover manifest UI model with the sol 0. The update to 2021-02-18. And the photo number to 54. Rerun the test, this time it should pass. Because my function will sort the list, I will add a second item to verify the order. In the given part, I will add a manifest photo remote model with a list of cameras. Define the update to 2021-02-19. This is all to 1 and the total photo to 201. In the expected result, add the rover manifest UI model with the sol to 1, the RDEV to 2021-02-19, make sure you use a string for the sol. The number to 201. Rerun the test and see the result. The test fails because the items are not in the right order. If I go to the rover manifest converter and remove the sort, the test will pass. I don't want to modify my converter, so I will revet the change and continue to use sort. Then I will invert the item in the expected result to match the fact that the latest stall should be on top of the list. Then restart the test and it should pass. Stay tuned for view models and repositories. In this video, we will create a test for the Mars rover manifest view model. We will use MockK. MockK will allow us to redefine the call for the repository under the view model, an error on demand. First, I will move the rover's manifest converter test inside a package domain model. Then create a package UI manifest list. Inside this package, we will have the file for the test of the rover manifest view model. Then create a file MainCoroutineRule. This file is the main dispatcher. In the app Gradle file, we will use test implementations to add coroutine tests. Write test Linux Kotlin coroutine test 1.7.1. And sync the project. Once the project is synced, get back to the MainCoroutineRule. We will create a val test dispatcher as a test dispatcher. Then initialize it with the unconfined test dispatcher. This unconfined dispatcher is a test coroutine scheduler and can control time and manage running coroutine within a test. Extend the class with the text watcher. Then override the function starting. At the end of the function, add dispatches set main test dispatcher. Then also override the function finished. And add dispatcher reset main. Then I will modify the rover machine provider. In the app module, we will create the annotation @IO dispatcher to use it to inject the IO dispatcher. And then the annotation @qualifier. Then create the annotation class @IO dispatcher. Inside the object add modules, use the annotation @IO dispatcher, then provides, then create the functions provide IO dispatcher as a coroutine dispatcher, then initialize it to dispatcher.io. Then in the Mars rover manifest ViewModel, in the constructor, add the coroutine dispatcher by using @IO dispatcher and create a private val IO dispatcher as a coroutine dispatcher. Then use it on the ViewModel scope inside the launch called the IO dispatcher. It is always better to call a network request on the IO dispatcher as it provides more threading options than the default dispatcher. Then start the app and verify that nothing is broken. The app should be working as before. Now create a file Mars rover manifest ViewModel test inside the UI manifest package under test. In order to use the MainCoroutineRules, create a rules and call it CoroutineRule. In order to use MockK, we need to import it as a test implementation. Write test implementation IO MockK with the MockK version name. Then go to the project Gradle file, add MockK version 1.13.5. To solve an error log, we will need to add slf4j. So add test implementation group org.lg, name slf4j simple and the version to 2.0.6. Then sync the project. Back in the Mars rover, create a private val Mars rover manifest repo. Initialize it using MockK class. And define the type of Mars rover manifest repo. Then use add test to create a test function. Name this function should emit error when error. Because we are in a coroutine, we need to use run test CoroutineRule's test dispatcher in order to run our code tests. This will make sure that the coroutine we launch in our code will be executed before we run the assertion of it. From the given part, I will use coEvery for MockK. And the function getMarsRoverManifest with the parameter perseverance on the Mars rover manifest repo. Each time I will call the getMarsRoverManifest with the parameter perseverance, I will return a flow of rover manifest UI state error. Then I will initialize a Mars rover manifest ViewModel. I will pass it the mocked repo and the CoroutineRule's test dispatcher. On this newly created ViewModel, I will call the getMarsRover manifest with the string perseverance. Then I will create a val result. As the rover manifest UI state from the ViewModel. I will use first to take the first item of the state flow. Then I will use assert equals to verify that the result is a UI state error. Then run the test, it should pass. Now if I change error to loading and I rerun the test should not pass. Revert the test to Then I will write a second test called should emit success when Repo returns success. As we launch a coroutine on the tested functions, we should use run test and the text dispatcher. For the given part, I will create an expected result as a rover manifest UI state success. Inside this rover manifest UI success, I will create a list. The first item will be a rover manifest UI model with the sol 1. The Earth date 2021-02-19. And the photo number to 21. I will create a second rover manifest UI model with the sol 0. The Earth 18. And the photo number to 54. I will use coEvery to define the getMarsRover manifest answer. This function will take perseverance as a parameter and return a flow of the expected result. Then I will create the Mars rover manifest view model. For the parameter, I will pass the MockK repo and the CoroutineRule's test dispatcher. Then I will call the get Mars rover manifest with the parameter perseverance on the view model. Then create a val result and initialize it with the rover manifest UI states. Use first to collect the first item of the flow. Then use assert equal to compare the expected results. Then run the two tests. The both should pass. Now I want to make the test fail to make sure it is correct, so I will insert a typo inside perseverance. Because nothing is mocked on a repo for that parameter, the success will never be emitted. Then revert this change to make the test the way we want. Those two texts will guarantee that the view model behaves correctly, in error or in success. In this video, we will create a test for the Mars rover manifest repo. Inside the test package, create a package data. Create a file Mars rover manifest repo test as a class. We will create a MockK for the manifest service. Create a private val Mars rover manifest service. Initialize it with MockK class. And specify the type to Then we will define the coroutine rule. So use @getRules and create a val coroutine rule, initialize it with the MainCoroutineRule. Then use the annotation @test to create a function. Name this function should emit success when manifest. This function will be in the context of a coroutine, so use run test and apply the coroutine rule with our test dispatcher. Create a val rover manifest remote model. Initialize this rover manifest remote model with a photo manifest. Define the landing date to 2021, 02/18. The launch date to 2020, 07/30. The max date to 2023, 05/19. The max sold to 799. The name Perseverance. We will define two photos. Use manifest photo remote model to create one. For the camera, define a list of camera. Define an off date. A sol 0. And a total photo of 54. Define a second photo with a manifest photo remote model. Define a list of camera. Define the RDF to 2021 02/19. The salt to 1. Define the status active. Define the total photos number. Use Coroutine to define a behavior for the getRoversManifest service. Each time we call the getRoverManifest with the rover name Perseverance, we will return the rover manifest remote model we have just created. Now to the when part of the test, we will create the Mars rover manifest repo with the mocked service. Then we will create a val result, call the getRoverManifest with the string Perseverance, and get the float to list. Now we will create an expected result as a rover manifest UI state success. Manifest UI model. The first one with the sol 1. The Earth date 2021-02-19. And the photo number to 201. The second one with the sol 0. The Earth date 2021-02-18. And the photo number 254. Then use asset equals to compare the expected result with the result. For the result, take the first item of the list. I also want to make sure that the result size is to 1. Then run the test, it should be working. If I change my expected result, the test should fail. Make sure you revert that change. Make sure you have the correct import for assertion or JUnit assert. Then we will create a second test for the failing case. Create a test function should emit error when manifest service throw timeout exception. Use run test with our CoroutineRules test dispatcher. Use Coil to define the response for the get Mars rover manifest with the rover name Perseverance. This time, throw a timeout exception. For the when part, create a Mars rover manifest repo with our mocked services. Then create a val result. Then call the get Mars rover manifest with the rover name Perseverance. Form the flow to a list. Then use assert equals to verify that the result site is 1. Use a second assert equals to verify that the first item of the result is a rover manifest UI state error. Then run all tests of the Mars rover manifest repo tests. Both tests should pass. In this video, we will create a test for the Mars rover photo view model. If this is not the case, make sure you have a package UI and a package manifest list inside it. If not, correct it. Inside the package UI, create a package photo list. Inside the package photo list, create a class Mars rover photo view model test. Then open Mars rover photo view model. We will refactor it with the IO dispatcher. Use the annotation @IODispatcher to create a private val IODispatcher. Then replace dispatcher.io with the IODispatcher, all inside the get Mars rover photo function. Then you can clean up some imports. Then get back on the Mars rover photo ViewModel test. Create a private val Mars rover photo repo using MockK class and the type Mars rover photo repo. Use add_get_rules to create a coroutine rules. Initialize it with the MainCoroutineRule. This rule will allow us to use coroutine inside our test. Create function should emit success when repository emits success. Use run test coroutine room test dispatcher to use coroutine inside this test. For the given part, create a val expected result as a rover photo UI state success. For the parameter rover photo UI model list, create a list of rover photo UI model. For the first rover photo UI model, create it with the ID 1, rover name Perseverance, image src http example.com photo 1, sol 0, update 2022-03-10, camera full name camera 1, and is saved to true. Create a second item rover photo UI model with the ID 2, rover name Perseverance, for the image src https example.com/photo2, the sol 0, the earth date 2022-03-10, the camera full name Camera 2, and is those are example data. You can replace them with something you want. Then we will use query to define a return for the get Mars rover photo. Use the parameter Perseverance and the sol 0. Then return a flow of the expected result. For the when part, create a val Mars rover photo ViewModel. Initialize it by creating a Mars rover photo ViewModel with the Mars rover photo repo and the CoroutineRule test dispatcher. Then call the get Mars rover photo with the parameter Perseverance and the sol 0 to match the one in the co-every clause. Then create a val result. Initialize it with the Mars rover photo ViewModel rover photo UI state first. For the then part, use assert equals to compare the expected result with the results. Then run the test. It should pass. Then we will create a test for the error case. Create a function test name should emit error when repository emit error. Use equal run test with the CoroutineRule's test dispatcher to use coroutine inside this test. Use Coroutine to define the return of the get Mars rover photo with the parameter rover name perseverance and the sol 0. We will return a flow of rover photo UI state error. Then create the Mars rover photo view model with the Mars rover photo repo and the CoroutineRule test dispatcher. Then call the get Mars rover photo on the view model with the parameter perseverance and the sol 0. Create a val result and initialize it with the Mars rover photo view model rover photo UI state. For this end part, use insert equals to compare the rover photo UI state error to the result. Then run this test. This time we will use to run this test with coverage. Running the test with coverage will allow us to see which part of the code are tested or not. You can go on the Mars rover photo view model and see that we had tested the first function get Mars rover photo, but not the change save status. We will do this now. Then create a test function called should remove photo when photo is saved and change save status is called. Use run test with the CoroutineRule test dispatcher to use coroutine in this test. Create a val model with the ID 1, the rover name perseverance, the image src http example.com/photo1, the sol 0, the off date 2022-0310, the camera full name camera 1, and the isSaved true. Then use Coroutine to define the behavior for the remove photo functions. It will return unit as unit is an empty function. Then create the ViewModel by calling Masterclass Photo ViewModel with the Masterclass Photo repo and the CoroutineRule test dispatcher. Then call the change saved UI status with the rover photo UI model. Because this function does not call any result, we will use coverify to verify that we call the repo with the run again all tests with coverage. All tests should pass. Go to the Mars rover ViewModel and see that the case for the saved photo is not covered. Duplicate the last test. Change remove to save. And is saved with is not saved. Change the boolean is saved to false. You can also modify some parameter in the rover UI model. Modify the Coroutine to use the save photo instead of the remove photo. Modify the coverify to use save photo instead of the remove photo. Then rerun all tests. The 4 tests we have just created should pass. Also have a look on the ViewModel, all lines should be covered. In this video, we will create a test for the Mars rover photo repo. In the test folder, inside the package data, create a Mars rover photo repo test. Create a private val Mars rover photo service and initialize it with a MockK class using the Mars rover photo service as a type. Create a private val Mars rover save photo DAO. Initialize it with the MockK class and the type Mars rover save photo DAO. rules to create the val CoroutineRule and initialize it with the MainCoroutineRule. Create a test should emit success. In this test, we will make the service to return a valid response and a DIO to return some saved photos. Use run test to run coroutine inside this test. Use coroutine rules and the test dispatcher. Inside the given part, we would create a val rover photo remote model. For the photos parameter, create a list of photo remote model. For the first remote model, create a camera remote model for the camera parameter. For the full name of the camera, define camera1, the ID 1, the name camera1, and the rover ID 1. The earth date 2022-07-02, the ID 2, the image src /photo1, For the rover, create a rover remote model with the ID 5, the landing date 2021-02-18, the launch date 2020-07-30, the name of the rover Perseverance, the status active. For this all, define 20. List, so copy and paste the first remote model. Then change camera 1 to camera 2. Change the ID to 3. The camera 1 to camera 2. The image SRC with photo 2. We will use Coroutine to define a response for the get Mars rover photos on the Mars rover photo service. Make it to return the rover photo remote model we have just created. A return for the all save IDs on the DAO. Make it to return a flow of a list of ints. Create a single item too. Second photo remote model has an ID of 4. This configuration will define that the first photo is saved and not the second one. For the when part, create a Mars rover photo repo, initialize it with the service and the DAO. Then create a val result and initialize it with the get Mars rover photo. Use toList to create a For the then part, create a val expected result as a rover photo UI state success. Initialize the rover photo UI model list as a list of rover photo UI model. For the first rover photo UI model, define the ID to 2. The rover name to Perseverance. For the image src, https example.com.photo1. For the Sol 20, update 2022-0702, the camera full name camera 1, and is saved true. Define the second hover photo UI model with the ID 4, the hover name Perseverance, the image SR photo 2, the Sol 20, the Earth date 2022-0702, the camera full name camera 2, and is saved to false. Make sure the Sol is defined as a string. Use assert equals to verify the size of the result is to 1. Use the second assert equals to compare the expected result and the first item of the result. Then run all tests for the Mars rover photo repo. The assertion is not working because I have made a typo on the camera 1. Fix it and restart the test. Now it should work. We will create the test for the error. Create a test function should emit error when service throw exception. Use query to define getMaskRoverPhoto behavior. When the service is called with perseverance and sol 0, throw a timeout exception. Use also query to define a behavior for the all ID saved on the DAO. When the sol 0 and the rover name perseverance is passed, return a flow of list of int of 2. Inside the when part, create the Mars rover photo repo with the service and the DAO. Then create a val result, call the getMarsRoverPhoto with the parameter rover name perseverance and the sol 0. Use toList to convert the flow to a list. For the then part, use asset equal to verify that the result size is 1. Use the second asset equals to compare the first item of the result list with the rover photo UI state error. Then run the test. The test should pass. We will write a test that verify we call insert when we save the photo. Create a test function should call insert when save photo is called. Then use run test with Coroutine test dispatcher. Create a rover UI model with the ID 2. The rover name perseverance. The image src https example.com/photo1. The sol 20. The earth date 2022-0702. the camera full name camera 1, and is saved to true. Create a Mars rover save local model with the rover photo ID 2, the rover name Perseverance, /photo 1, the Sol 20, the Earth date 2022-0702, the camera full name camera 1. Use query to define the insert rover save local model is passed, return unit. Unit is an empty function. Create a Mars rover photo repo with the Mars rover photo service and the Mars rover save photo DAO. The save photo with the Mars rover photo UI model. Use coverify over the function insert with the parameter Mars rover save local model on the DAO. Then run the test should pass. Then duplicate rename the function shulkDelete when remove photo is called. Replace insert with delete. Then call the remove photo function. Then run the test. The 4 test should pass. We will now create a test to test the getAllSaved function. emit UI model when all data are retrieved. Use run test coroutine rules test dispatcher to use coroutine inside our test. Create a Mars rover saved local model list as a list of Mars rover saved local models. For the first item, use rover photo ID 2. Rover name Perseverance, img src https example.com/photo1, sol 20, the earth date 2022-0702, and the full name camera 1. Create a second Mars rover saved local model with the rover photo ID 4, the rover name Perseverance, the image src https example.com photo 2, sol 20, earth date 2022-0702, and the camera full name camera 2. Then use Coil to define a behavior for the get all saved on the DAO. For this function, return a flow of the Mars rover save local model list. For the when part, create the Mars rover photo repo with the service then create a val result as a response for the get all saved. Use first to get the first item collected. For the then part, create a val expected result as a rover photo UI state success. Define the list of rover photo UI model list as a list of rover photo UI model. For the first, use the ID 2, the rover name Perseverance, the image src https example.com photo 1, sol 20, earth date 2022-0702, camera full name 1 and is saved to true. For the second item, duplicate the first one, change the ID to 4, the image src to example.com/photo2, and the camera 1 to camera 2. Use assert equals to compare the expected result with the result, and run all tests. 5 tests should pass.